Hello everyone, in this lecture I'm going to solve one example of SVD, singular value decomposition, and see how we can actually use that. And after that I'm going to talk about principal component analysis and how it is related to SVD. Okay, so let's get started. So what I want to do here, this lecture, we want to find the SVD for the singular value decomposition for this matrix for A equals to 3, 4, 0, 5 square matrix of 2 by 2. Okay, so this is our question. Okay, now let's start solving that. So this is our question. So the first thing I want to do is for SVD to find the eigenvalues of, you see that this is SVD, so SVD was giving us this U sigma times VT. So the first thing that I want to do is to find the, find the step 1. First, find the eigenvalues of A transpose times A. So this is what we do. So let's solve that. So ATA, what is that? So the transpose of that, this is the transpose 3045, then multiplied by A 3405 will be 25 20 20 25. Okay, so this would be my AT matrix. Now I want to find the eigenvalues of this, so I need to calculate the determinant of AT times A minus I. The identity matrix should be set to 0. So let's solve that. We'll get 25 minus lambda, 20, 20, 25 minus lambda. The determinant of that equals to 0. So this will give us this equation, 25 minus lambda square equals to 20 square. So then we will have two roots here. Lambda 1 is 45 and lambda 2 is 5, right? So these would be my eigenvalues for this problem. Okay. So this gives me the singular values of A for the SVD. So let's calculate that. So the singular value of A would be, we show it with sigma. Sigma 1 would be square root of these eigenvalues. So square root of 45 and sigma 2 would be square root of 5. Okay? So then I can simply construct my sigma matrix. So my sigma matrix would be square root of 45 0 0 square root of 5. Okay, so this would be my sigma matrix. Okay, so I found my sigma matrix. Now the second thing I need to find is the step 2 to find the other U and V matrices to be able to complete my SVD. So the next thing I will do is step 2. I need to find an orthonormal basis of A. Of an orthonormal basis of eigenvectors of AT times A. Okay, so these eigenvectors of this matrix we can have many different eigenvectors, but we want an orthonormal basis of those vectors. Okay, we need to keep that in mind. That is how the SVD is actually constructed. So let's start finding that. So to find the eigenvectors, first I will find it for lambda 1, which is 45. So I just write this down again. So my matrix would be 25, 20, 20, 25. This was 80 times A times V1, which would be x1 and x2 here, I can say, equals to 45 lambda times x1 and x2, right? Okay, so this gives me this matrix. So now I solve this equation, two equations. So I will get 25 times x1 plus 20 x2 equals to 45 x1. The second equation is 20 x1 plus 25 x2 equals to 45 x2. Okay, so the first one I will get from the first one is these two cancel out, so I get 20 x1 here. So the first equation here gives me x1 equals to x2. If I do it for the second one, the second equation, again I get a similar equation. Okay, so x1 equals to x2. So now my general first eigenvector is x and x, right? Okay, but I want an orthonormal basis of that, so I will make sure that it is orthonormal. So let's first find the second one, then we can choose which values of x I need to use. So for the second one, we have lambda 2 now is 5. So we get I will just use this again. Don't need to write this down again. So let me just use it. Okay. Okay, so lambda 2 is 5. And then I have this set of equations. So let's see what we get now for this set of second equations. So again, we get 25 25x1 plus 20x2 equals to 5x1, and 20x1 plus 25x2 equals to 5x2, right? Okay. So this time, let me actually write this in y. So we have two different things. We write this in y. Okay. I don't want it to be mistaken with the above one because this is another vector. y2, y1, y2. So 25 y1, 20 y2 equals to 5 y1, 20 y1 plus 25 y2 equals to 5 y2. Okay. So this is my equation. So now these two cancel out. I get 20 y1. Same thing here. I get 20 y2. So all of these give me this equation that y1 equals to minus y2. Okay. So the second set that I am going to get and consider, the second eigenvector, is minus y and y. Okay, so this is my second eigenvector. Okay. Now, I want an orthonormal basis of this. So we need to make sure that this basis that we create is an orthonormal, and that will create my V matrix, okay? Which would be in this, let's see here, this VT matrix, okay? It's an orthonormal matrix, and I have already found the sigma matrix, and then I just need U matrix, okay? So let's see what we get here. So I want an orthonormal basis. So what I will get is V equals to, I want now this to be an orthonormal basis. So so the vectors that I am going to choose is as follows. So V1, I will choose it as, should be normal. So if I choose 1 and 1, let's say x equals to 1, then I need to divide it by their square root of their magnitude, so it becomes orthonormal. So for V1, I choose 1 over square root of 1 and 1. And for V2, I will choose the same thing. If I set it to 1, I need to divide it by 1 over square root of 2. So this becomes an normal basis. So then this gives me the V matrix that I was looking for, which would be 1 over square root of 2, 1, 1, and minus 1 and 1. Okay, so this would be my V matrix. Okay, so now I found that. Now step 3, I want to find step 3. Now find U matrix. So what is U? So the first column of U, let's first find the first column and then the second column, and then we will find out the whole thing. So the first column of U is gonna be this sigma 1 to the minus 1 times AV1. And why is that? Why is that? You can actually find it very simply from the definition of the the definition of the SVD, okay, and eigenvalue vectors. So the reason is that if you remember, in the A, we said it's gonna be U sigma VT, and again, because this is VT is orthogonal matrix, so I can assume that when VT is an orthogonal matrix, what does that mean? If you go back to the definition of orthogonality, you can you can see that that means that equals to V itself, right? V minus 1, V minus 1. Okay, so that's the definition of orthogonal matrix. So now what I'm going to do. So let's see that. Yeah, so because VT is an orthogonal matrix, so I can say this equals to V to the minus 1, and then multiply both sides by V. What will I get? I will get AV equals to U sigma, right? So now this is, what does this mean? Now I have this U sigma, so it is similar to an eigenvalue problem again, right? So I can say that AV1 here, from here, I can say it's sigma 1 U1, right? So for just a first vector, for just the first vector, after if I just want to find the first let's say column of that, I can just write it based on the colors, like AV1, AV2, or U2. So this will give me U1. You just need to multiply it by sigma 1 to the minus 1. Then you will get this U1, okay? So this is how we find U, right? We find U. First, we find each column by column in this example. So let's start here. So U1 will be first, I need to write this matrix here, sigma, and then multiply it by the first vector of V1. Okay, so that gives me that matrix. So sigma 1 to the minus 1 I need to also do that. So what is sigma 1? We have it here. It's 1 over square root of 45. So let me write that. So 1 over square root of 45. That would be my sigma 1. Then I have the A matrix. What was A matrix? The original matrix that I had in this problem set is 3, 4, 0, 5. Let me check. 3, 4, 0, 5. So let me write this down. 3, 4, 0, 5. And then multiplied by V1. What is V1? We have it here. 1 square root of 2. 1 over square root of 2. So simply this 1 over square root of 2, 1 over square root of 2. Now, you calculate this. What do we get? We get 1 over square root of 45 times 3 over square root of 2. And the second one is going to give me 4 plus 5, 9 over square root of 2. So in total, I will have this. I can write it actually here. 1 over square root of 10, 1, and 3. So this will be the first vector of that, okay? Now for the second vector, I can do the same thing. So let me do it. So for the second vector, again, we have AV2 equals to sigma 2 U2. So I can say that U2 is basically sigma 2 minus 1 AV2. So what do I get? If you calculate it, I am not going to repeat it again. This would give me this 1 over square root of 10 minus 3 and 1. Okay. So finally, my whole U would be as follows. 1 over square root of 10. U1 is 1 and 3. And U2 is minus 3 and 1. Okay. So now I have everything. I have U, I have V, and I have sigma. So I can actually reconstruct my whole SVD. So my whole SVD is as follows. It's going to be as follows. So A could be represented as follows. So what is U? Is 1 over square root of 10 minus 3 over square root of 10, 3 over square root of 10, 1 over square root of 10. Okay, so this is my U. Sigma, square root of 45, a diagonal matrix, 0, 0, square root of 5. And what is my VT? Or V, I can just write V and then the transpose of that would be VT. So my V, we found it here. Let's check what was it. It's this, 1 minus 1, 1. So it's going to be 1 over square root of 2 minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. Let me just check if it is correct. Yes, it's correct. So this gives me my whole SVD decomposition, this is U, and I need actually to add a transpose here. So this would be sigma matrix, and this would be V. T, the whole thing is VT, okay? Okay, so this is how actually you can find SVD. This was one example. So first you need to find the eigenvalues 80 over times A, then you find the orthonormal basis to find V, and after that you can find U, the vectors of U, and then it will give us the full eigenvalue, singular value decomposition. Okay. Now, I want to talk about very, very important application of this SVD. It's very important, especially being used in recent machine learning algorithms. It's one of the very famous ones. And let's see how this can really help us to better reduce the dimensionality of some of the huge metrics and data. So the next topic that I want to talk about is principal component analysis or PCA. So those who have done machine learning might have been familiar with this PCA. Now I want to see, and I want to say actually how this is related with this SVD that we learned. Actually, SVD provides one of the best algorithms for PCA, and I will say why, because it actually works for all rectangular matrices, and it's very computationally efficient. So let's see first what is PCA, or principal component analysis. So it's actually a linear transformation technique. So a linear transformation technique to reduce dimension in machine learning. So it's one of those machine learning methods that is used to reduce the dimensionality of the data, or the dimensions of the, especially when you have huge data sets. Okay. So what does it do? So it finds principal components that are orthogonal and capture the mean dynamics, the mean variance, actually, the max variance, the maximum variance. What does that mean? It means you find the principal components that are both orthogonal and they capture the maximum variance of the data. You want to reduce the dimension, but also you want to capture the maximum variance that is possible, that we can represent with these reduced dimensions. Okay, so the way it works is as follows. So typically, what do we do? One of the algorithms, and in these algorithms, algorithm, it's the general algorithm of PCA, is as follows. So first, typically, the first step is you center the data. What does that mean? You subtract mean of each column, or average of each column of your data. Okay, so this is the first step. Second step, you compute the covariance matrix. What is covariance matrix? Let's go through that. So the covariance matrix is as follows. Imagine you have X, which is a matrix of n by p, where n is the number of samples that you have. And p is the number of features. Okay? So now, the covariance matrix is as follows. The covariance matrix would be C, which is 1 over n, xt, the transpose of that matrix, times itself. So this gives me a covariance matrix. So, okay. The next step is to find eigenvalues and eigenvectors of C. So what are eigenvalues here? So the eigenvalues, if you look at this covariance matrix, because it's already subtracted, we already subtracted the mean in each of the columns. So if you calculate this, this will give us what? Something similar to variance, okay? So this would be, the eigenvalues of this matrix would be actually representing the variance of the data. And what are the eigenvectors? The eigenvectors here are basically the principal directions. Okay. So now, what's the next step? In the next step, once you find these, you just sort the eigenvectors by descending e-values. So what does this mean? This means that we sort based on the higher e-value to lower e-value, and then we sort the e-vectors for that, because the higher e-values means we capture higher variance in the data, okay? And finally, the last step, we project data onto top k e-vectors. Basically, we select the top k vectors and then project the data, and this gives me my reduced dimensions or dimensional space. So my space is actually reduced, and this can give me a representation of that reduced dimensions, which are having the highest variance in data, can capture the maximum variance. Okay. Now, what we can do is, instead of using a general C or covariance matrix, what we can do is we can use SVD. Now, this will simplify our calculations, and also it would work for all the matrices, and it would give us a very nice representation. So let's see how SVD can help us here. So instead of using the covariance matrix, we can use SVD, singular value decomposition. Let's see how that works. So in this setup, we will have X. We can just represent it with SVD as U times sigma times VT, right? This would be my data. So I will bring everything in my data like this. Then, what would be my C? The C matrix, which was my covariance matrix, I can show it as this 1 over n xt times x. Just substitute this x here. What I will get is 1 over n. xn, xt would be v sigma t transpose and x transpose based on the u transpose based on those properties of transpose. Then I have u, my original x, which would be sigma vt. What is ut times u? It's identity matrix because it's orthogonal. And it's orthogonal matrix, so ut times u will become I. Then what this gives me? This gives me 1 over n times v times sigma transpose times sigma times vt. Okay, so this will be my covariance matrix. And what is this? Sigma t times sigma. It's a diagonal matrix, so it's basically, if you multiply it, it's just square root of sigmas. So it's just sigma 1 square, sigma 2 square. These are 0 up to the end. So what I'm getting is as follows. I will just get v sigma square over n times vt. Okay, so then this is giving me a very interesting formula, and that is, here I can see that what are the eigenvalues of my covariance matrix would be, basically here it's written sigma square over n. Right? And what would be my eigenvectors? So eigenvectors of C would be basically the columns of V. It's very, very interesting and nice property. You can see it here. Right? Why? Because here you can see, if you just multiply it by V, we get back to that eigenvalue problem that we were actually looking for. And so let's see that. So let me actually show it here. So here in an eigenvalue problem, we have this C. So if I multiply that both sides of here, let me show. Okay, if I multiply both sides here in this equation, if I multiply both sides by V, what do I get? So I get V equals to sigma square over n times Vt times V. What is Vt times V? Because it's again an orthogonal matrix. It's a very nice property of this SVD. It's an orthogonal matrix, so it's just going to be identity, right? So the right hand side would be identity. Let me actually, I have another term here. Got to write it down. So I have CV. The right hand side would be identity. So I get back to this nice matrix, which is basically like that. If I wanted to find the eigenvalues of that, so each of that would be like CV1. Each column would be one of those eigenvalues, right? So this will give me back that my original like eigenvalue relationship. So this is a nice property of this this matrix, right? This SVD decomposition. So there is one way to check it if this is correct. So let's do it. I can actually check it here. So this was a brief thing. Let's do it very more thoroughly. Check. So we take one column, VI of V. So let's see what do we get. So I get CVI equals to one over n xt x times VI. Just write it down, 1 over n xtx VI. What was xt over times xi? We just showed that. I can show it with xt x. I can just show it with this u sigma times vt, right? This was my SVD. So let's write this down. Write it down, u sigma. U sigma is gonna be u sigma times, I'm not gonna write it down because we have already written it here. So it's gonna be this. So let me just copy that. Actually, it's easier if I do that. Okay. So we get this. Okay. So now, what would be CVI now based on this? So we can get CVI equals to 1 over n xt times x times VI, which is going to give me V sigma square over n V transpose times VI. Okay. So what is this now? So this would be basically, I can just show it here. So V is basically my orthonormal basis is V1 to Vn, right? this is an orthonormal base. And then what would be Vt times Vi? So Vt times Vi is basically V1t Vi up to Vn transpose times Vi. Okay, so this would be Vt times Vi. And what is Vt times Vi? So Vt times Vi, because it's an orthonormality, I can use this orthonormality property. It would be 1 when if I equals to j, and 0 if I does not equal to j. Okay? So what does this mean? This means that Vt times Vi is basically the identity matrix, the ith column of identity matrix, or EI, which would be the ith column of identity matrix. So now that I have that, so what do I get here when I write it down? So here, I will get sigma I square over n times Vi. Okay, similar thing to what we got there. So this gives me one, this would be the eigenvector, and this would be the eigenvalue. Right? So this proves what I was actually saying already. I already showed it before in another way, but this is kind of a formal way of showing that. Okay. So now let's review what do we have here, and what did we do to get here. So let's first review all this lecture. So we first started with single value decomposition. So what was single value decomposition? This was in the previous lecture. Given a matrix of A of size m times n, the SVD expresses it as follows. And then we showed this basically, SVD is basically a rotation, rescaling, and again rotation in space. And it's a generalization of the eigenvalue decomposition problem, or EVD. Sometimes we call this EVD problems, right? So let me just write it down here. EVD. Then we talk about EVD. Then we solved an example, and we showed for finding SVD, what you need to do is first you need to find the eigenvalues 80 times A. This gives us the sigma matrix. And then the second one, you find an orthonormal basis of eigenvectors of 80 times A. And then this gives us the V vector, the V matrix. And to find U, we just calculate this sigma minus 1 times AV1, and this gives us a column of that U matrix. And finally, we were able to build this SVD. And then we showed what is principal component analysis? A very important technique in machine learning, which is a linear transformation technique to reduce dimensionality in the data. And we showed that by it finds the principal components that are orthogonal and captures the maximum variance of the data. And it works as follows. So we talked about the algorithm that you need to calculate. You first need to subtract the mean of each column, so you only look at the fluctuations, and then you compute the covariance matrix and finding e-values and e-vectors of C, which gives us the top k e-vectors or principal directions and variances. And then we showed how we can actually use SVD here in the C matrix. If you just, for your data, if you do a SVD first, and your C matrix would be very simple. And the eigenvalues of your C would be basically sigma square over n, and the eigenvectors of C would be the columns of this V matrix, right? So, and we showed that this will give us a orthonormal basis, and these eigenvalues will give us the amount of the variance in the data, and we proved that it's actually the case here in two ways, one simple and a little bit more detailed way I showed in both of the ways. Okay, so that's it for this lecture and our overall matrix algebra overview. Thank you very much, everyone.